Let's get started. So fresh from PDC, we're delighted to have Anders here to give us an overview of C#. Anders.
Thanks. My name is Anders Hejlsberg. I'm a distinguished engineer in the developer division. I'm also the chief designer of C#, a language that we've been working on probably for the last 2 years or so, and which we just recently rolled out for public consumption, or at least the first public view of it at the PDC. These slides are actually pretty much the same slides that I gave at the PDC, so if some of you saw that, then you're going to be a little bored. At the end of the presentation, this presentation takes about a good hour, and then we have, another half hour or so where we can do Q&A and some demos maybe or whatever. So first of all, I assume that you're all familiar with the .NET framework, and I think that you've already seen some presentations on that. A lot of this presentation sort of assumes that you already sort of know some of the key premises behind .NET, the language neutral, common language runtime, garbage collection, type safety, zero install, et cetera, et cetera. Just sort of to frame, why a new language? What's the idea behind C#? Why did we go do this? And here are sort of the 4 key ideas that were on our board from the beginning. First, to create what I call a component-oriented language in the C and C++ family. I'll drill into some more details on each of these. Further, to create a language where everything really is an object, a truly object-oriented language. Enable our customers to write that next generation of more robust and durable software. And then finally, to preserve the investment that our customers have in skills and existing code and so forth. So going to the next level of details in these core ideas. We call C# the first component-oriented language in the C and C++ family. And what I mean by that is that core concepts of components are first class in this language. Those are things like properties, methods, and events, design time and runtime attributes, integrated documentation, and so forth. And you may ask, well, why is that important? I think if you look at what has happened to software development sort of over the last 5 or 10 years is that we're actually increasingly not writing big monolithic applications, but more and more writing smaller components that plug into hosting environments, be that embedded controls in a browser, code in an ASP page, stored procedures in SQL Server, transactioned objects that hook into MTS, and key to all of these are that all of these hosting environments are that they're sort of turning the world upside down. There's a lot of bidirectional communication going on between the hosting environment and the component that slots in. It's not just some app you start from a command line and all interaction happens with the user. And so concepts for components like properties, like methods, like events are really key, I think. Also, because the language is component-oriented, because all of these concepts are first class, it sort of enables you to do this thing I call one-stop programming, where you can embed it because everything is in one place. In this language, there are no header files, no idle files, no def files, no bunches of information that you sort of have to keep in your head and glue together yourself conceptually. Because everything is written in one place, code that you write in C# can truly be hosted in a variety of environments. A great example, of course, is ASP+, the next generation ASP, that allows you to write C# code directly embedded in HTML pages. Another one of our sort of four big ideas is to create a language where everything really is an object. Now, first of all, this is not a new idea, but I think there are some innovative ways that we've sort of realized this goal. I sort of tend to think that there are two traditional views of how you build type systems in languages. If you look at C++ and Java, they sort of divvy all types into two kinds of categories. There are primitive types that are like ints and floats, and they're magic. They have certain blessed capabilities, built-in operators, special code generation, and so forth. And then there are classes or objects that the user can create, and they have other capabilities, but there's sort of a disconnect between the two. Now, and of course, the community has long since realized that this disconnect exists, and certain languages have indeed also fixed it. If you look at, say, Smalltalk and Lisp, primitive types in there are objects indeed, but that comes at great performance cost. Now, Smalltalk will typically optimize, for the int primitive type, but if you're dealing with floats and doubles in Smalltalk, you are indeed allocating objects off of the GC heap for every temporary, value that you produce, say if you multiply two values. C# unifies these two worlds, but at no cost to performance. And I'll get into precisely how that works. And of course, this is not just a function of C#, but also, to a large extent, a function of how the .NET Common Language Runtime is built. But it definitely leads to a deep simplicity throughout the language. And of course, also, it gives you improved extensibility and reusability. Users can indeed build their own new primitive types, and we do, in fact, do that in the .NET base class libraries. There's a decimal type that gives you 28 digits with a base 10 representation, so you have no round-off errors, ideally suited for financial applications. There's a whole family of SQL types or database types that are nullable, and where you have, sort of that three-valued booleans, for example, that you know from databases. And then, of course, collections, etc., work for all types, because everything can be viewed as an object. Any collection type that exists can also be used with the primitive types. Allowing our users to build robust and durable software, obviously a very, very important design point. It sort of breaks down to certain things that the .NET Common Language Runtime provides, and certain things that the language itself provides. Of course, this language is garbage collected. Well, not of course, but it is, which means no memory leaks, no stray pointers. All error handling is built around structured exception handling. The language is type safe, provably type safe. There is no possibility of uninitialized variables or unsafe casts. The compiler will perform conservative flow analysis and issue errors if there's ever a chance of a variable being uninitialized. Those are the top three are actually in a sense provided by the platform. The last one, versioning, is an interesting thing. It's really sort of a very boring thing. It has to do with this sort of DLL hell problem that we've all experienced as Windows has gotten more and more complex, but also with what happens when you build software in a version 1 and then it evolves over version 2, version 3, version 4, and meanwhile this piece of software is built on top of some library that underneath you is evolving along a different temporal line and a different versioning sequence. What happens with this code? What do we do in the language to ensure that code doesn't break as your foundation evolves and the code itself evolves? And it's really interesting how pervasive this problem is when you sit down and look at language design from that angle. I mean, what can you do in the language to make sure that this works better? And I have some slides on that later that I'll get into. And then finally, a big idea has been to preserve the investment that our customers have in existing software and in skills, training, and so forth. First of all, C# has a very close C++ heritage, much closer than, for example, Java. We have not gotten rid of C++ features like namespaces, pointers, unsigned types, enums, and so forth, and basically have strived to make as few unnecessary sacrifices as possible. Furthermore, we've worked really hard to give this language great interoperability with existing software. It's really, in a sense, taking the stance that this is not an ivory tower. You know, you don't fall off a cliff the minute you can't do a particular thing within the box. Rather, we give you the ability, of course, to talk to XML, SOAP, and that's really mostly through the platform, but also COM, DLL, and any other .NET framework language. And finally, internally, we have, at this point, millions of lines of C# code in the .NET framework already written. And consistently, we've seen that our developers are reporting that, you know, it's a very short learning curve from C++, and they are consistently seeing increased productivity. So those are, you know, some of the big ideas. Of course, when you create a new language, you have to show people what Hello World looks like in that language. And here's the C# version of Hello World. It imports the system namespace, creates a little class called Hello with a main, and then writes Hello World on the console. Nothing really particularly surprising here. It kind of looks like C++. Just sort of starting off with what does the structure of a C# program look like? And there are some key concepts here that also sort of define how programs are nested, if you will. At the outermost level, programs are organized in namespaces, very much like namespaces in C++. And namespaces can contain types and other namespaces. Furthermore, namespaces are open-ended, so several source files can contribute to the same namespace. I can have a namespace foo, put a class bar in it in one source file, and then in another source file I can have namespace foo and put, you know, class X in, and they both go into the foo namespace. As I said, namespaces can contain other namespaces, so, you know, the whole thing nests, allows you to give nice logical names to all of your types, which are the other kind of thing that can go into namespaces. And types then, of course, are broken down into classes, structs, interfaces, enums, and delegates. And there are some interesting differences between C#'s view of classes and structs versus C++'s view, and I'll get into that. But so programs start with namespaces containing types, and then types in turn can contain members depending on what kinds of types they are. But sort of the grand union of things that types can contain are constants, fields, methods, etc., etc. I'm not going to read it off the slide there. One of the things that are interesting about C# is how source files are organized. In C# there are no header files, so there's no separation between declaration and implementation. It's all in one place. When you declare something, you also implement it right there. Code is written in line. I talk about that because of that. It makes the code sort of more mobile and more embeddable in various hosting environments. It also, well, another key point of how C# programs are organized is the fact that there is no declaration order dependence in this language. Indeed, conceptually, when you compile a program or a project or a library that you've written in C#, it's as if you give the compiler the list of all the source files that make up the project. You know, you give them on the command line or in a response file. Here are all the source files. You go concatenate them and then compile the whole damn thing and figure out all of the, you know, interdependencies and so forth. conceptually, that's how it works. Of course, the compiler actually does support incremental updating of already generated images, but conceptually, it's as if you just tell it where's all the source, and the thing figures it out by itself. This, of course, also means that you're free to arbitrarily merge and split source files and take classes out of one and put them in another without breaking your code. Here's sort of a little example of what a little stack class would look like in C#. First, we at the top here import the system namespace again, and then we say everything that goes from this curly to the one down here at the bottom goes into the system.collections namespace. And then we declare a stack class, and it has an instance variable called top of type entry, and then a push and a pop method. And you'll see that for error handling we use exceptions here. So it looks pretty familiar to C++ programmers. So I think key to understanding pretty much any programming language is how is the type system designed in this particular programming language. And so I'll try and get into C#'s type system here first. And right off the bat, there are two kinds of types in C#. Value types and reference types. And it sort of really directly speaks to the semantics of the types, whether they have value semantics or reference semantics. So value types are things that a variable of a value type directly contains the data of the type. So a good example is an int. When you declare a variable of an int type, you're setting aside, say, 32 bits, and you can store ints directly in that slot. And value types, of course, have no notion of being null. And then there are reference types, which whenever you declare a variable of a reference type, what you're really declaring is a pointer, if you will, a type-safe pointer that can be null or that can reference an instance of the given type. And a good example of that is the string class. And here, is just graphically how that lays out, Just drilling in a little bit more to these categories. Value types are the primitive types like ints and floats and doubles and so forth, enums and structs. And reference types are classes, interfaces, arrays, and delegates. And there are some examples here of, what does the syntax of declaring one of those look like. One key difference here you'll note between C# and C++ is that structs and classes have different semantics. A struct is a value type and has value semantics, whereas a class is a reference type and has reference semantics. C# contains a bunch of predefined types, but they're really just, as I say in the bottom here, they're really just aliases for system-provided types. So the int, the reserved word int in the language, is simply an alias for the system-provided integer, 32-bit integer type called system.int32. And it's indeed declared in our base class library. It has methods on it. It has operators and so forth. But anyway, just looking at what are these reserved words, reference types, there are object and string. Integral types, we have, the 8, 16, 32, and 64-bit family of signed and unsigned types. Characters are all Unicode characters in this language. Floating point, we have, the IEEE float and double, and then the decimal class I talked about earlier that is suited for building financial type applications. And then finally, there's a bool type. So drilling into the different kinds of types that the language provides over and above the primitive ones. Classes are single inheritance in C#, but do permit multiple interface implementation. The kinds of members you can have in classes are constant fields, methods, properties, indexers, events, operators, constructors, and destructors. Now, some of these you'll know from C++, some of them you won't, like properties, indexers, events are new concepts that I have some more slides on also. Members can be static members or instance members, meaning, there's one copy in the universe or one copy per instance of the class. And types can be nested within each other, and it's really just sort of syntactic naming sugar. There's pretty rich access, or pretty rich member access control in the language. Public, protected, private are sort of known from C++ already. There's an additional access specifier called internal that says this member is accessible within this compilation, but inaccessible elsewhere, meaning that as you compile, say, one project or one library, the internal members can freely be referenced between the different source files or different classes in that compilation, but are inaccessible outside that compilation. So as I said, there are some key differences in semantics between structs and classes in this language, unlike C++, where struct simply means change the default of all my members to be public instead of private. So structs are like classes, except they're stored in line, they're not allocated on the heap. Assignment of a struct copies the data, not the reference, so there's no aliasing. And there's no inheritance, or rather, more correctly, all structs implicitly inherit from object. These guys are ideal for lightweight objects. They sort of bridge the gap, as I said, between primitive types and sort of heavyweight stack or heap allocated classes. Examples would be, complex numbers, points and rectangles, colors, and so forth. It's interesting to note, actually, that all of the built-in primitive types in the system are indeed structs. So int, float, double are all structs. And there's really no difference between those structs and user-defined structs. Now, benefits of structs, of course, are there's no heap allocation, and therefore there's less GC pressure. And indeed, once you get down to really small objects, they make more efficient use of memory. Of course, there are also disadvantages. You don't want to have large structs, because every time you assign one to another, you're copying it, and that's, of course, a more expensive operation. Just, to really hammer the point home here with the semantic differences, here's an example of a point structure declared either as a class or as a struct. In both cases, the declarations actually look identical, except for the class versus struct keyword. There's an int x and an int y field in the class and in the struct, and then some methods, presumably, and they have a constructor. And then, indeed, I can, declare a variable of the class type and assign it a new class point, or I can declare a variable of the struct type and assign it a new struct point. But really what happens when I do this is that for the struct implementation, when I declare the SP variable, I'm just setting aside, in this particular case, 64 bits or 8 bytes of memory with enough room for 2 ints, and that's it. Whereas for the class version, I'm setting aside, the size, whatever the machine size of a reference is, and that reference can either be null or can reference a heap allocated object that in turn has a vtable identity and so forth. Interfaces are a first-class concept in C#, and they do support multiple inheritance, but of course they do not support implementation inheritance. Interfaces can contain methods, properties, indexers, and events, and furthermore we have some interesting features like private interface implementations that allows you to implement interfaces on classes without publicly exposing the members that you are using to implement the interface. Like, let's say, for example, you want to implement some data-bound interface, and this is some sort of internal worker interface that data-bound UI controls want to implement, and that's, an example of the declaration is here. And let's say I'm creating some sort of UI control called edit box that inherits from control and implements the iDataBound interface. I can implement that interface in one of two ways. I can just have a method that has the same signature. i.e. a method called bind that takes an idata binder, or I can explicitly implement idatabound.bind and say, here is the implementation of the bind method in the idatabound interface. Now, there are two key advantages to this. First of all, this method here is not part of the public interface of EditBox itself, or the public set of methods of EditBox itself. So the fact that I'm implementing this interface is actually not visible to anybody, and so I don't end up polluting my public protocol with implementation details. A second advantage is if I want to implement two interfaces that so happen to have the same method with the same signature, this gives me a way of doing that.
Isn't EditBox required to have a bind implementation?
Excuse me?
Isn't EditBox required to have a public bind implementation?
No, that was precisely what I was saying here, that no, it's not. If it has a public bind, so basically there are two ways it can satisfy the interface implementation. It can either have a public bind method, or it can have a private explicit implementation of idatabound.bind, in which case it doesn't have to have a public bind, in which case you're not polluting the public set of methods of EditBox with an implementation detail, if you will.
So EditBox can claim to implement idatabound without having one of idatabound's required public methods?
Yes, and indeed, what happens then is when you're using EditBox is that in normal use it appears not to have this method, but if you cast it to idatabound, the method is there. It is castable to idatabound, and then the method is there. So it does have the method, it's just not publicly accessible.
Well, but that is a way.
Through the EditBox, it is publicly accessible once you cast it to idatabound. C# has enums. Unlike C++, they're strongly typed in C#, which basically means there are no implicit conversions to and from int with respect to enums. And basically, that in turn means that that you don't end up making the common error of passing the wrong enum type to say the wrong parameter. Because in C++ every enum is just another way of writing an int, you really don't get the additional type checking. Enums support operators like plus, minus, etc., etc. So you can add two enums and produce another enum of the same type, for example. And then furthermore, we permit you to specify the underlying type of an enum, which can be any integral type. It's one of the strange things about C++ is that all enums are 32 bits for some reason. Even if you don't need more than 3 bits, you still end up wasting. Delegates are a little more novel. They're like object-oriented function pointers. At least that's how I usually think about them. So you're familiar with function pointers in C++, which is just a pointer to the entry point of a function, and the type of the function pointer incorporates the signature of the function that you're calling through the pointer. Delegates are like that, except that delegates are like bound member function pointers. So a delegate can first of all refer to a static member or a normal function, but it can also reference a particular method of a particular object. It is in a sense a combination of a reference to an object and a reference to an entry point of one of the object's methods. And when you invoke through the delegate, that this pointer of the invocation becomes the object that is also stored in the delegate. So it's a way of referencing a method of a particular object. And it actually turns out to be precisely what you want for event handling. Say you have a button that has a click method, and really what you want to be able to say is, when the user clicks this button, call this method of this object over here in a type-safe fashion, please. And that's what these give you. So they're the foundation for events in the .NET frameworks. There are some nifty things about delegates. A delegate internally actually is just that, a pointer to a member, a pointer to an object and a pointer to a member function of the object. However, externally, a delegate appears to have an invocation list. And an invocation list is, in a sense, a list of methods on objects to call. And we permit you to use the plus and minus operators to create these invocation lists. So you can take a delegate and add another delegate to it. And you now end up, when you call through that delegate, first calling the one function and then the other function in the order that you plus them together. This sounds a little weird at first, but it actually turns out to be really useful for multicasting scenarios in eventing. And internally, the runtime will cook up little code stubs that makes this very, very efficient. Okay, so here are some examples of how you declare delegates. For example, here's a mouse event delegate, and really what I'm declaring here is a type named mouse event that represents a method taking an int x and an int y and returning void. And here's another one, a function that takes a double and returns a double. To create a delegate, I simply instantiate onto either a static method or an instance method. In this case, this might actually be a static method, the sign method of the math class. And now, from there on, I can invoke it, just like I invoke. Well, actually, it's a little simpler than invoking in C++ because I don't have to use a star to dereference. Okay, so getting back to this type system unification I talked about earlier. As I said, in this language, everything is an object. Or at least everything appears to be an object. All types ultimately do inherit from object. And what it, of course, if you don't think about how that precisely works, the implication is that any piece of data can be stored, transported, and manipulated without any additional work. If you have some sort of conveying mechanism, a queue component, say, well, of course you would expect that thing to be, say, able to queue an object and dequeue the object. And of course you can queue and dequeue user objects that way, but you can also queue and dequeue ints or any primitive type that you care to. Now, so here's just sort of hierarchically what it means. We have the root object type, and of course, we have a bunch of reference types like streams and hash tables, but also int and double appear to inherit from object. And the question, of course, is how does that work? And it works through a mechanism that we call boxing and unboxing, or indeed that academia also calls boxing and unboxing. If you just go with the sort of rule that everything inherits from object, well then that means it is possible for me to write code like this little snippet here, where I first declare an int and assign it the value 123, and then because int inherits from object, there's an implicit conversion of int to object, so I can assign that int to an object. And indeed, later, I can downcast the object to int and take the int out again of the object, so to speak. Now, what actually happens is, what actually makes this work is a mechanism known as boxing and unboxing. And so if you look at graphically what happens when I execute this little piece of code, well, first I, get myself an int variable and stick the value 123 into it. When I do the assignment of the int to an object, the system boxes the int. So it goes and allocates an object, tags that object as being an int, i.e. sets its v table, if you will, to reference the int type, sticks the value 123 into it, i.e. copies the value from this int into the box, and then returns that with the static type object that you can now carry around. And indeed, this guy is self-describing, so later, when I do the downcast, the system will perform a dynamic type check, see that indeed I'm holding an int in a box here, and if so, we'll copy the bits out, otherwise we'll raise an exception. Benefits of this, well, there are many. First of all, you don't have to write wrapper classes that allow you to treat primitive types like objects. Any primitive type is an object, and any piece of data you can treat as an object. As I said previously, it means that collection classes work with all types, although there are some performance implications sometimes. Another, if you're sort of an OLE automation aficionado, ever written any VB code or C++ code that talks to OLE automation, one wonderful thing here is that variant goes away and becomes object. There is now one type of thing in the system, and it's an object. There are lots of examples of use of this in the .NET frameworks. Take, for example, the formatting function provided by the string class that allows you to give a format specification where you sort of use placeholders for the arguments and optionally also give formatting information in those placeholders. And then it simply takes a variable number of objects. And even if I am formatting, floats or doubles or dates, well, if they're not reference types, they simply get boxed and passed in as objects, and at that point, they're completely self-describing. Indeed, they're self-describing to the extent that they can implement interfaces. So the int type actually implements an I-formatable interface. And that's indeed what the string formatting function does. It turns around for each of these objects and asks them to please format themselves into a string. Is there a question down here?
What happens if you try and unbox a null object?
That gives you an exception. Right. Yeah. Null is not in the domain of any value type, so it's an exception to try and unbox a null. Another example is, the hash table type that we have in the framework. It has an add method, that takes two objects, a key and a value, and indeed I can use ints as keys, and they just get boxed, and so I can use it, as a way of looking up, a numeric value to a string representation, as I've illustrated here. Okay, so getting back to component development, I said up front that the things that define components to users are things like properties, methods, and events. It's integrated help and documentation, and it's the ability to attach design time or runtime information to the component that any hosting environment of the component can then query and understand how to treat the component. And C# has first-class support for all of these. Our support is not naming patterns like get blah and set blah or adapters that try to turn events into interfaces. Rather, they're first-class things. Also, they're not external files like IDL files that describe marshalling or anything of that nature. And so really the bottom line is that components are very easy to build and consume in this language. Now, C++ of course has methods, but C++ does not have properties or indexers or events. So I will try and just sort of drill into those capabilities. The way to think of properties is really sort of to think of them as smart fields or abstract fields. If you look at a field or an instance variable in an object, well, it really sort of has two things it can do. It can load a value or it can store a value. You can read a value from the field or you can write a value into the field. Properties are like that from an external point of view, except you actually get to write code that controls what it means to get or set the value. So the syntax for declaring a property, let's say I have a button, which is again, one of my UI controls here, and I want the button to have a caption property. Now, to implement this, I first give myself some internal storage, a string that can store the caption. Note this is lowercase c here. And then I have an uppercase caption property. And it sort of looks like a field declaration, except it ends with an open curly. And then I have a get and a set block in which I specify the code to be executed when I get the value of the caption or set the value of the caption. Indeed here, whenever I get the value, I just return what I'm storing in my instance variable. But when I set it, well, I stuff the new value in there and then I repaint the control so that when the user assigns, immediately the image of the button is updated on the screen. And of course, it means that I can write code that looks like this, create myself a new button and then assign a caption to it, or read what its current caption value is. Now, as you can see, the syntax is pretty natural here. You can omit the get or the set, and by doing that, you end up with a read-only or a write-only property. You can have virtual properties, so the accessors can be virtual. You can override in descendant classes what it means to get or set the value of a property. And you might say, well, geez, this seems like a very costly way of emulating fields. Does that mean that every time I assign or read the value of a property, I have to make a method call or execute code? But in reality, it doesn't, because we turn this into IL, and then our JIT compiler will inline small pieces of IL and indeed make them every bit as efficient as a field access. So in this particular example where I'm reading the caption here, that will literally just turn into a load of the caption field in the object, because the inliner kicks in and removes the method call. However, from an external point of view, I am much more versionable. I can change the implementation of this getter or setter without affecting any code that already exists and is already compiled. So it gives me much more flexibility in managing my internal storage and my APIs.
Value here is a reserved word.
Value is, well, it's not a reserved word. It's an additional parameter that is provided in the set block.
You don't have to declare it?
You don't have to declare it. No. It's sort of like this.
What's its type?
What's that? Its type is the property type, so it's string in this case. So it's the new value that you were assigning. And it's an additional parameter, just like this is an additional parameter of type button, if you will. So, yeah?
Can you have properties of value type?
Oh, absolutely.
So
Yeah.
you have primitive methods for like inc and decrement and stuff like that, or is it only set and get?
Oh, I see. No, it's only set and get. However, if the type supports the plus plus operator, you can indeed, let's say you have a count property on your list and it's a read-write property. You can indeed say list.count plus plus, and that will get, increment, and set.
But nothing special for plus plus.
No, but you can, no, the plus plus is not tied to the property, it's tied to the type of the property.
Okay.
Of course, we have operator overloading, you can implement plus plus, but there's nothing magical about it with a property. So just like properties are sort of like smart fields, indexers are like smart arrays. Just like properties give you the ability to say, when I use the syntax object dot some name, so do indexers give you the ability to say what happens when I say object bracket something, i.e. when I index the object. They're in a sense like overloading operator brackets in C++, except overloading operator brackets in C++ always has to return a reference, and that really it kind of becomes problematic when you have associative arrays where you actually don't have any piece of data to return. So instead, we have these indexers, and they're really a lot like properties. As you'll see in this example here, taking my UI paradigm further, say I have a list box I'm implementing that inherits from my base UI control, and it has a list of items that it's showing. So I get myself some internal storage here to store the string array that makes up my items. And then I can declare an indexer for the list box of type string indexed by int. So this guy defines what does it mean to index a list box with an int. Well, it means that the result is of type string. It is read-write because I have a getter and a setter, and here are the actions associated with it. Either fish out the nth or the indexed item, or store into the indexed item and repaint the list box. And that means I can write code like this over here. Now, indexers can be overloaded. So you can overload on the argument types. For example, you can have an associative array, and you can say what it means to index by int or to index by key, say string, is one example.
primitive string there is always a traditional dense array?
String is
The indexing of string creates a primitive dense array there.
no, it doesn't create anything here. Actually, all I'm just saying is what does the syntax mean? It is up to me to manage the internal storage. Is that what you're asking?
Well, you're saying item subindex equals value,
Uh-huh.
and you're not
Oh, here.
doing anything right.
Oh, okay.
The implementation.
Oh, okay, fine. Yeah, I already have some string array that I've already internally allocated. You see lowercase items here is my internal string array, right? And I've set that equal to some array I've allocated. Now, typically here, I mean, I would have some range checking and whatever, you know. So it's just, you know,
It's not
I didn't want the slide to
It's
get
not like
too
you're
big.
getting a built-in
No,
associative
no,
array
no, no,
implementation.
no, not at all, not at all.
Can you overload on return type?
No, you cannot overload on return type. Which actually is a limitation of well, Com Plus allows you to overload on return type, but I don't really, or the .NET framework or the Common Language Runtime or whatever we're calling it these days.
C# itself is not allowed.
That's correct. That's correct. Okay. Okay. Finally, events is a new concept as well. If you programmed in C++, and events sort of, you know, have two sides to them. There's the sourcing of events, i.e., being a someone that fires off events, and then there's the consuming of events. And I'll try and look at both sides of the picture here. If we start with the source, in order to be an event source, you must first declare a delegate type that defines the signature of the event. In our case here, I'm declaring a delegate called event handler that represents a method that takes an object sender and an events args and returns void. And having done that, I can now say in my button, declare a click event. And I do that simply by declaring public event handler click. And this looks a lot like I'm declaring a field of a delegate type, and indeed it is very similar to doing that. So in a sense here, the button simply sets aside space for a delegate with that signature. And now, in order to fire the event, I simply check, is anyone listening, i.e. is my delegate non-null? If so, invoke it with the appropriate arguments. Now, on the consumption side, if I now want to handle the click event from this button, I would typically do that in a form. I would have a form that contains the button, so I would inherit myself a form from the base form. I would declare a button instance variable. In my constructor for the form, I would instantiate the button, assign to its caption property, and then create a delegate onto my own method called OKButtonClick, which has the correct signature, and then simply use the plus equals operator on the click. Because it's of a delegate type, and because delegate supports plus, I can now use plus equals to attach an event handler. And indeed, I could use minus equals to take the event handler away again. And I can attach many by doing multiple plus equals. And of course, I mean, the net effect of all of this is when the user clicks the button, you know, control arrives here. And it prints out, you know, a message to that effect. I want to point out that this perhaps looks expensive, or I don't know, you know, I mean, it certainly looks new. It looks different. Delegates are extremely efficient. Indeed, a call through a delegate really just turns into a, you know, push this pointer and call the method. So it's a couple of machine instructions to do a delegate invocation. So on the order of a normal method call is the cost of doing an invocation.
Do you support pattern matching for delegates? For the arguments?
What do you mean by pattern matching?
Say a type that's
Oh, currying, or is
an object is inherited from some other object. It happens to be that the argument matches to its inherited.
Okay. So you mean covariance on the object type or on argument types?
There's some.
Yeah.
Like in.
I mean, there are two things that we could do that we haven't done. This is the short answer. One is currying, and the other is argument covariance. We do neither. So currently, we only support identity of the argument types, and there's no currying. But we could do both. Just for those of you who don't know the currying concept, it's basically the notion that, let's say I had a delegate. Let's say my click, indeed, let's say my OK button click method here only had one argument, and let's say that no, I'm confusing myself. Yeah, let's say it only had, let's say it had 3 arguments: the sender, the event args, and one additional argument. You could imagine that when I instantiate the delegate, that I supply that additional argument, and that's stored along with the delegate, and then when the invocation happens, you know, the caller supplies some of the arguments, and the arguments curried away in the delegate supply the rest. And that's something we're looking at doing, but we don't do it currently. You could also imagine that my OK button click, for example, had the, let's say event args is a class that, of course, ultimately derives from object. You could imagine that OK button click had the signature object sender, comma, object args. And indeed, it would be type safe for me to delegate onto a method that expects a less derived type. But we don't currently support that. There are some interesting issues with doing that generally, in that we might have to inject code stubs that boxes value types and whatever. So either you sort of accept the asymmetry of it only applying to reference types, or you do the work, and we just haven't really made a decision on that currently.
Are you thinking of doing parameterized types and parameterized methods, or?
I'm not familiar with what.
Parameterized types as, you know, like templates in C++.
Oh, you mean like generics or?
Yeah, I mean.
Yes. We, in fact, I was going to talk about that at the end, maybe, if you don't mind, because we have been working indeed with some of the MSR researchers from Cambridge on precisely that. Okay, so let me try and move along here. Attributes is basically a whole new thing. I haven't really seen this notion in any other programming language, at least not to the same extent before. Basically, let me start out by framing it. You know, what are they good for? Well, imagine when you're building code that you often find yourself, and particularly as we go more and more towards component building, in situations where you want to associate additional declarative information with types and members. For example, you know, what is the documentation URL for a class, or the transaction and context for this method, or how does this class map to XML? How does this field within the class, does that become an element in XML or an attribute in XML, and so forth? And there are millions of other examples of this sort of need to attach additional declarative information. Currently, we of course permit you to say whether a method is public or private or protected, but you may want to have your own kind of thing, you know, up that same alley, right? Traditional solutions to this problem have been that you either, you know, add keywords or pragmas to your programming language and it's sort of a close-ended solution. You know, we as language designers get to control what kinds of things you can say on types and members, and that's the end of that. Or another widespread solution is to use external files and basically have it be an associative thing. You know, you write a class and then you write an IDL file that gives you the, you know, the COM mapping or the Corba mapping of that thing, and then you better sort of match it all up. So our solution is this thing called attributes. I think that the best way to look at attributes, first to look at an example of attributes in use. We have this thing called web services that we've been pushing pretty heavily at the PDC, and that the whole .NET framework is sort of built around this concept of web services, i.e. Using the internet as the carrying layer for method invocations, really, is sort of what it boils down to, and using XML as the format for carrying messages and results. Now, one way that manifests itself is that we provide some attributes that people can use to put on their methods to indicate, when you write a class, now you want to turn that class into a web service, and so you want to indicate some of these methods should be accessible over the web, or they should be web methods. So you do that by putting a web method attribute on your method declaration. And it's almost sort of up the alley of, yeah, it's public, and no, it's a web method also. Now, in this particular example here, this web method takes a purchase order, which is a class, and of course that thing will ultimately need to be carried along as XML, and you may want to say something about how it maps to XML. Indeed, you want to say, that when you make it into XML, call the root tag order and put it into this XML namespace. And then, by the way, this field here maps into an XML element called ship2 and bill2 and blah, blah, blah. But the date maps into an attribute in XML. Of the order, well, of the enclosing, I mean, so now we're just, getting into XML semantics, which is really not what we're talking about here. We're talking about the mechanism whereby you can convey this type of information. And so attributes, basically, if we talk about what you can do with them, is you can attach them to types and members, and then you can examine them later at runtime using reflection. You can walk up to the reflection objects that represent this class, this method, and ask, do you have this particular attribute? So that's sort of what you can do with them. Now, the way they work is that attributes are classes. They are classes that inherit from a predefined class in the system called system.attribute. And that class has no instance data, so it's just sort of a placeholder in the hierarchy, and then all attributes hang off of that. So basically, if we go back to the example here, there is in the base class framework a class called web method attribute, and XML root attribute, and XML element attribute, and they all derive from system.attribute. Now, furthermore, these classes have constructors. Indeed, XML element has a constructor that takes a string. And web method has a parameterless constructor. Now, what we do when you use attributes is that we in a sense pickle away this thing that goes in between brackets here is like a constructor. It's almost like you said new XML element of a string. Instead of generating code for that, of course, first of all, we type check it and compile time check it and all of that. And assuming that everything is valid, we then pickle away the arguments and put them into metadata instead of generating code. And then they sit in the metadata until someone walks up and asks for them. And so at the point where you walk up and through reflection ask for an attribute, we can first of all, we have a naming scheme for the attributes. It's just class names. We have a way of asking for them through reflection. And indeed, we have a way of instantiating them because we can instantiate an instance of that, provide the arguments that were pickled away in metadata, and in a type-safe fashion, convey the information back to the user. So you sort of see how we're leveraging the type system in order to give you an extensible attribution mechanism. These things are extensively used in the .NET frameworks. Of course, you saw here XML and web services, but we also use them for security, serialization, component model, so forth. There's a question over here.
The example that you gave, one of the parameters was prefixed by a name.
Yes, yes.
Is that a general facility for all method invocations?
No, it's a general facility for attributes. And basically what that means is that we pickle away in metadata. Well, first of all, XML root must have a namespace property that is readable and writable. And what we then do is we pickle away that information in the metadata, and then when we reconstitute it at reflection time, we invoke it calling the constructor XML root of order, and then we set the namespace property, and then we hand you that back. Over here.
So these attributes are each attached to one item, like
Yeah.
a field or a class. Is it possible to have an attribute that connects two different items in your program, like two different fields?
No. they always hang off of something, either a class or a type or a member. However, you can hang many of them off. I mean, there's nothing to say that I couldn't have two XML element attributes on one field. And indeed, I could even name the other field. I mean, and you could somehow build up a mechanism yourself. But there's no way of sort of grouping things together just so you can hang an attribute on the group, if you will, that we don't provide that ability.
Well, I was thinking more in terms of having an attribute which says something about how two fields relate to each other.
Right. You would typically do that by hanging the attribute on one field or on the other field or on both.
Yeah.
Is how you would do that. Yeah?
To do all of that is, can you specify a type rule that says that like an XML element attribute has to be inside the scope of an XML root attribute?
No, you cannot. There's a lot more that you could do with this that we're not currently doing. Basically, the only constraints you can put on things is when you declare an attribute, you can put an attribute on the attribute, a meta attribute, if you will. Yeah, okay, I know people's heads start spinning when I get into that, but basically, there's a meta attribute that you can use to specify what kinds of things can you use this attribute on, like methods, types, blah, 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 blah. There are a couple of other things you can specify there, whether the attribute inherits or not, and whether it's multi-instance or not, meaning whether you can have multiple of them on a single member. Future things that you could imagine doing with this, of course, you could imagine instantiating these attributes at compile time and allowing them to do validation of their arguments and of other attributes that might be present, you know, in the program code. Indeed, you could even imagine going as far as instantiating the attributes and allowing them to do syntax tree transformations on your code. But perhaps it's getting a little too far out. You know, we have not really made any decisions about how far we want to take this, but it's certainly something we're thinking about. Okay. XML comments. So one of the things I personally find very important, and one of the things that Microsoft traditionally has not done a very good job of, is documentation and the ability to tie together implementation and documentation. We've traditionally had a dev team and a UE team, and never shall the twine talk. And you know, you end up with stupid documentation that talked about the foobar method obtains the foobar of the blah blah, you know, and you have no idea what it does. So we've focused on giving users the ability to write source within, or documentation within their source code. And of course, that immediately then brings about, well, what should that meta language look like? And we could go dream up, you know, yet another language for writing documentation. But what we did instead, what we said, it can be anything as long as it's well-formed XML. And so basically what we say is that if you prefix comments with 3 slashes, well, 2 already makes it a comment, right? But if a comment starts with 3 slashes, then, and if you throw a switch up to a compiler that says gather up all of the in-source documentation, then the compiler will validate that there is well-formed XML in this contiguous block here. And if not, it'll issue an error. It doesn't actually care about what tags you use in here. That could be up to your organization. You may want to document one way, and someone else might want to document another way. However, we will validate it. And there's a few other things we will do that, in a sense, are hard-coded, like expanding references that you make to other elements in code, and so forth. I actually have a little example of this that I might want to try and show you. So here's an example of an XML parser. Indeed, it's some of the source code for our XML parser in the system. And you see it has bunches of XML comments that document this API. I can compile this, and I can specify, please take all of the XML and stick it into t.xml. And that produces then, if I start t.xml, so fire up the browser on t.xml, it produces this whole tree here Let me try and bump up the font. So you can see that, here's some of the stuff that I actually wrote in source. The block class provides a static method, yada, yada, yada. You see these summary remarks and whatever. The compiler puts additional XML around that, that specifies what member did this come off of and what assembly was it in and so forth. But it's all well formed. The compiler has already checked that. Indeed, I could actually, if I fire up, here's another little source file that I have that contains an XSL transform style sheet. I can copy one line out of this guy here and fire up c.xml and paste that one line in here. So now I took the compiler's output and I added one line that references a style sheet for this XML that transforms it into nicely formatted HTML. So if I save that and then refresh the browser, you'll see that all of a sudden now it's nicely formatted, and I can actually use this to read the documentation of the source code that I just compiled. So that's another nice extensible way of doing documentation. Okay, boy, gosh, we're running behind here. Statements and expressions. Maybe I'll just say here that we have very high fidelity with C++ in terms of the statements and expressions in the language. We fix some of the well-known and irritating problems in C++, like no separation between the bool and the int type. So you can say stupid things like if I equals 1, and that's always true, and assigned 1 to I. We say that an if, while, or do must have a bool condition, and so if I equals 1 is an error. It has to be if I equals 1. We say gotos can't jump into blocks. We say that the switch statement does not have fall through. Now, first of all, you can write multiple case A, case B, case C, case D, but once you write code, there can be no fall through to the next block of cases. However, and basically, as long as you write well-formed normal C++ code with no fall through, then it is still valid. You, in a sense, we say you must have a break at the bottom of the code in a case statement. And if you don't, it is an error if, by conservative flow analysis, we determine that control could possibly get to that point. Now, if you want fall through, you must insert a go-to case or go-to default that goes to another case or to the default, indeed indicating your intent here. This also means that, well, first of all, it means that you don't get these fall-through things. And I actually dug around on the internet and found this little story about how an AT&T switch took the entire New York phone system down for 8 hours because of a fall-through in a case statement that kept, just rebooting the system. So it is actually a real-world problem. Now, one additional advantage of this, by the way, is that you can now freely reorder your switch statements because there's no dependency between the blocks of code, because the intent is always captured in each block. Okay, additionally, we have a for each statement that allows you to iterate arrays and user-defined collections. We have checked and unchecked statements that allows you to control overflow checking in arithmetic operations. And we have a rule that says expression statements must do work, or in more technical terms, there must be the possibility of a side effect of an expression, otherwise it is an error. And that is sort of the flip side of the if I equals 1. We say it's bogus to write I equals 1 and throw away the result. So the for each statement allows you, first of all, to iterate arrays. Given an array, like in here's, main that takes an array of, a string array of your command line arguments, you can simply, for each string s in args, write out s. And that just iterates the elements of the array. But more importantly, you can also iterate user-defined collections. And we base that on a pattern. If if the type implements an enumerator, then the for each statement can work on that type. So as opposed, we could have looked at it differently. We could also have said, well, if it implements I enumerable, but the problem with that is then that everything sort of, because we don't have generics, it degenerates down to type object always, whereas by looking for a pattern, we can actually keep it type safe or strongly typed. The language supports parameter arrays, and they're really, in a sense, like the type-safe version of var args. Var args are great and very powerful in C++, and they're also extremely dangerous because it's a way of giving you the ability to walk up the stack and poke at memory that, very possibly is not yours. With parameter arrays, you get the same functionality, but in a type-safe fashion. And so for example, you can write your own printf in C#, and you would indeed do so by declaring printf that takes a format string, and then the last argument you can apply. If the last argument of a method is of an array type, then you can apply the params modifier, thereby indicating that it is a parameter array or a variable argument array. And if you do so, then when you write code like this, we actually turn it into code like that, where we instantiate an array, stick the arguments in, and of course, because we have boxing, anything goes when you declare the type to be object, and we just box the arguments. The neat thing, though, is that these are typed. You could actually say, that I can take a variable number of ints, as opposed to var args in C++, which is always untyped. Operator overloading, yes, it's there, and it really permits you to write, first-class user-defined data types, and there are plenty of examples of this in our base class library. I talked about the decimal type. There's also a date-time type and a time span type that defines, conversions between the various types, and you can subtract two date times and get a time span, and you can add a time span to a date time and so forth. It's used in our frameworks, it's used in SQL integration, and so forth. It's simplified from C++, mind you. C++ has some odd rules. You can declare sort of a global friend operator that changes the meaning of plus between two doubles. And now from there on out, and the rest of that compilation, plus with two doubles means something different. And that's clearly not a particularly versionable thing to do, or a controllable thing to do. So we constrain operator overloading to say that a declaration, operators are always declared as members of, or as methods of classes, or static methods indeed. And in an operation, x op y, the operator that we ultimately invoke must either have been declared in x or in y, or have been inherited in x and in y. It cannot come from some third unrelated place. And it's quite remarkable how it really, I have yet to find an example of where that constrains you, but it certainly outlaws all of these weird things that you can do. Here's some examples of what it looks like. Let's say I'm declaring a nullable int type, which is an int, that can also have, it's a database int that can also have the value null. This is one example of how I might implement it. First of all, I implement it as a struct because I don't want it to be heap allocated. I have a value field, and I have a bool that says whether the value is defined or not, and then I can have an isNull method that says, return whether or not it's defined. I can declare a plus operator that takes two db ints and returns a db int. And I can declare implicit and explicit conversions. In this case, an implicit conversion from a regular int to a database int, and an explicit conversion the other way. And it allows me to write nice readable code like this. Versioning. I talked about that. I better kick it up a notch here. I talked about that a little earlier. And I think I'm just going to jump straight to an example here, because I think this really sort of illustrates what I'm talking about. Let's say we ship, we being, say, Microsoft providing a base class library, we ship a class library containing some base class. And in version 1, you know, it doesn't have a lot of functionality, as you can see. The user then builds a derived class that inherits from base, and the user has determined, you know, empirically through feedback from his users that foo-ness is a very important thing, and you definitely must have a foo method on your class, and so he introduces a foo method. And then through popular demand, we determined that, gosh, foo-ness is becoming really popular out there. In version 2, we're going to put a foo method on our base class. And now the code looks like this. And the question is, what happens here? What happens, say, if it's written in C++? What happens if it's written in Java? Well, the interesting thing is that it always goes wrong in those languages. It goes wrong in different ways, but then the right thing never happens. In C++, first of all, there's no binary versioning. You can't just walk in and add a method and expect anything to work. But if you look at source code versioning, C++ incorrectly assumes that this virtual method in the derived class is an override of a virtual method in the base class, which clearly is wrong because it wasn't there to begin with. So that can't be right. But that's what you get. In Java, things sort of limp along from a binary perspective, but it does the right thing. Again, it does what C++ does. It assumes that this is an override of the base method. Indeed, in Java, sometimes things go even worse, because if we had introduced this foo method up here, but had it return type int instead, then Java would flatly refuse to load this stuff, because it first of all incorrectly assumes that it's an override, and then second keels over because the signatures are incompatible. Now in C#, this code continues to work. And in this particular example, there are now two foo methods. There's a foo in the base and there's a foo in the derived. The derived foo hides the base, which is fine, because it wasn't there when derived was created to begin with, so it's not like derived has any dependencies on that foo method. So from a binary perspective, things continue to work. You can dump a new version of base with this new method without breaking anything. If you recompile the derived method, we issue a warning, not an error, but a warning that says, warning, you are hiding an inherited method. You get the error here. The code continues to compile, continues to run, but you are warned that something funny is going on. And you can get rid of the warning by putting a new directive on the method that says, yes, I mean to hide this method, so shut up about the warning. You could also determine that, gosh, this foo method that I'm inheriting from the base is really cool. I'm going to rev my derived class and make it require version 2 of the base, and then I'm going to override the method. But only if you put an override directive on the method is it considered an override of the base method. There's never any inferencing going on over a barrier that evolves different temporally or from a versioning perspective, and that's where C++ and Java gets in trouble. Now this is one example of how versioning sort of affects your language design. There are multiple, surprisingly many places where this enters into the equation. The method, constructor, and whatever overload resolution rules in the language are affected by this and are different than C++ in order to have better versioning semantics. You saw an example of interface implementation rules where we permit you to do explicit interface implementations and implement methods with the same name from different interfaces. The way we handle var args or the parameter arrays, there are some interesting issues in there as well with respect to versioning. It's quite amazing, how it shows up everywhere and how it's really never visible to the user unless you do it wrong. So it's one of those boring features, but we've done a lot of work on that particular thing. Conditional compilation, I'm not going to say a whole lot about that other than, yes, we support conditional compilation. It is restricted from C++. We don't support macros. So, macros are basically the death of any rat tool. You know, the minute you can have macros, it is impossible for a background compiler to try and figure out what your code means, because you can change one character and the entire code now means something different. So we support a limited form of conditional compilation, and then we support this thing called conditional methods that maybe in the interest of time I'm going to skip over right now. And then finally talk about unsafe code. So I talked about earlier how we really try to do a good job of interoperability in this language and in this platform, really. So we have great, I mean, you know, any class you write in C# is automatically a comma object, and any comma object that's been written before can be directly imported and become a class in the .NET framework. Also, any DLL that exists out there, you know, you can call the entry points just by putting an attribute on a method declaration. And so the net result really is that you don't fall off a cliff if you want to use code that's already been written before. And we think that it's really important that we try and preserve that investment in existing code. However, there are cases where even those interoperability features don't quite cut it, you know, where there's some ugly existing API with some gnarly structs that contain pointers to unions or what have you, you know, that you want to call, some unmanaged code, and you want to be able to call it, and for that reason you really need to use pointers. Or you want to be doing some direct manipulation of things that are mapped into memory, or what do I know, you know, low-level stuff. Now, we could, of course, take the ivory tower approach and let you fall off the cliff and write it all in C. But by doing that, you actually make the world more of an unpleasant place to be, first of all, for the programmer, but also you actually open up even bigger security holes than if you try to stay within the box. So what we say is, you can stay within the language, you can stay within managed code, but you can do unsafe things that are not type safe. However, because we're staying within the box, we're well aware of the fact that you're doing this. We can tie it into the security system. We can control, you know, the downloadability, or rather non-downloadability of this code unless you have full trust. And we can also be more efficient about it, because the fact that we allow you to write unsafe code within the language doesn't mean that the code isn't managed. The garbage collector still understands what's going on the stack frame. It can still do GCs, you know, while the unsafe code is running. So you don't have to marshal, you don't have to erect barriers on the stack as you exit out to native code. So there are a lot of advantages to having this feature. Unsafe code is basically like having inline C in C#. Not C++, but inline C. You can allocate buffers off the stack, you know, like I'm doing here, and you can do pointer arithmetic like I do here. You can shoot yourself in the foot if you want. I mean, that's you know, this stuff is unsafe. Perhaps a more interesting example is, you know, a little snippet of code that I grabbed out of our framework. This is our encapsulation of a file, and you know, we have the abstract notion of streams in the framework, of course, and we have an implementation of a file stream that encapsulates a file in the OS. And to sort of see how that's been implemented, well, first, ultimately, we end up calling out to the Windows API to implement this. We could call out to some other API, but in this case, the Windows API. And the way we do that is we use a DLL import attribute here to import the read file method from the kernel 32 DLL. And when we declare its normal prototype, and it has pointers in it, but of course we want to give users a type-safe encapsulation of that. We don't want to require that they write unsafe code in order to use this file API. So we want to have a read method on a file that takes a byte array and an index and a count. But we want to implement it in terms of something that takes pointers down here. Now, in order for this to work, there are some interesting issues you run into. First of all, this byte array here is a managed array, which means the garbage collector might run at any time, and since it's a marked and compact garbage collector, it might actually move the object in memory. And so if I start obtaining pointers to these movable objects, things can go terribly wrong if the GC runs, and forget about ever finding out what happened, because the minute you put the debugger in there, your memory is slightly smaller and it doesn't happen at the same time. So it's, you know, it can be really poisonous. However, again, because we're not like falling off the cliff, but rather staying in the box, we actually have a statement that allows you to bridge the gap here. So in an unsafe context, and you put yourself in an unsafe context by using an unsafe keyword on a method, there's an additional statement available to you called fixed that allows you to fix a GC'd object and obtain a pointer to the first byte of the object. And that's indeed what we do here. So we fix this buffer, we pin it down, and now we know that it ain't going to move for the duration of this block, and now we can do pointer arithmetic and so forth. I'll get right back to you. I just want to point out one thing that occurs here with this fixed thing, is that this statement is basically, for all practical purposes, free. It doesn't actually do anything other than just put things into a table that describes to the garbage collector that should a GC operation occur whilst this code is executing, do not move what this variable points to. So it's declarative pinning, if you will. In 99.9% of the cases, there is no cost to the statement because a GC operation is not going to occur here. Now, of course, you have to be careful with this statement. You can create islands in the heap and whatever, and we will prefix this with all of the appropriate warnings. But it is nonetheless a very, very useful feature to have, because ultimately the rubber has to meet the road, and that's kind of the thing we're giving you here. Sorry, you had a question.
It seems to me that you're moving the problem that you described with the debugger to the case where the programmer omitted the fixed keyword.
No.
So can't the compiler figure it out?
Well, first of all, we're not really moving the problem because the user cannot obtain a pointer to something movable without using a fixed
statement. So you get
statement.
an error if you don't have the fixed
Oh yeah, you cannot say byte star p equals buffer
unless
it occurs in a fixed statement.
Okay.
Now what we cannot do is we cannot keep that reference from escaping outside of the curlies.
Right.
I mean, as much as, and that's basically because it's unsafe code, right? But at least, we don't allow you to shoot without aiming.
So
okay.
Is there a question? Is there an implicit assumption that when you exit the fixed scope that your unsafe code is not holding on to the
Yes,
pointer?
there is.
Because otherwise your GC is just going to die.
Absolutely. Yes. And ultimately, it's unsafe code, right? Caveat emptor. But yeah. But at least we make it, we make you think before that happens, hopefully. Tony?
Yeah, back in that example, who's responsible for bounce checking the buffer?
There is no bounce checking once you obtain the pointer, so the programmer is responsible. Now, if you...
So as written, that's bad stuff. It's
Uh,
not bounce checking.
that is correct. Oh, yeah. I'm sorry. Yeah, all error handling has been omitted from this example in order to fit it on the screen. Yes. But you're right.
You should put that little annotation.
I should. Yes. Okay, here are some extra or some additional information you can find. You may want to jot down these URLs. There's the little home page for the C# dev team. There's the URT home page where you can download the .NET SDK. You might want to go look at the PDC site that has all of the slide presentations that were given at the PDC, and there's some interesting ones in there with a lot more information on .NET itself. And then finally, you asked about, or someone asked about generics. I think it was over here. We've been working with Don Syme and Andrew Kennedy in Cambridge on a generics implementation in the runtime and in C#. And if you're interested in that, go to their little page here and check it out. They've come a long way. I mean, they've really done some remarkably great stuff. And there's a specification for how generics enter into the virtual object system in the common language runtime, and there's a genericized version of the C# compiler, and we're right now trying to determine whether we make a hard push to get generics into V1. I think that is unlikely to happen. We would like to do so, but we probably will do it in V2. We're over time. I can still take some questions unless you all have to go.
support the continue statement?
What's that?
You support the continue statement?
Yes, we do. Yes.
So from within an unsafe code region, you can get a pointer anywhere in memory, including objects that are in the safe region.
That's right. That's right. Yeah, pointers, I mean, the pointers you use in unsafe code are just like pointers in C. They can point to anything you want. Let's go over here.
You said at the beginning that the C# is type prove it, please.
Unless you have unsafe code. Okay.
How do you do?
Okay, well, we have a verifier in, it's actually not, it's, the verifier proves it. Assuming there are no bugs in the verifier. The bytecode verifier, yes. Ultimately basically what ends up happening is that we do a lot of the work in the compiler, like we perform conservative flow analysis to figure out, for local variables, whether they're definitely assigned. We have all that logic in place. I'm not saying there aren't bugs in it, but we do that level of verification. Then we emit IL, and then the verifier will also verify that the IL adheres to their rules. But of course, it's only provable to the extent that there are no bugs. Yeah.
Can I take C# and build comp components?
Yeah, actually, anything you write in C# is automatically a comp component. And of course, as long as you stay within the .NET framework and you use like C# or VB7 or managed C++, you don't ever need to have type libraries and registration and all our gunk, and H results and add reps and all of that crap. I mean, you just use the classes, But we can extrude a type library for any .NET class. And there's a tool that does that and can register it and do all of the sort of mumbo jumbo that needs to happen.
Yeah, it seemed to me you support asynchronous GUI events. Do you support threads?
Yes, well, in the language we have a lock statement that allows you to treat an object as a monitor, but that's all we do in the language itself. But the base class library in .NET has a whole bunch of thread support. But it's really more of a platform issue than a language issue. Yeah?
How are asynchronous system level exceptions handled? Are they translated?
Which, you mean like, which
Access
one?
violations?
Yes, they're all. So this is actually more, again, of a runtime question than it is a language question. But the runtime integrates with structured exception handling in Windows and transparently transform, with structured exceptions in Windows into .NET exceptions and vice versa. So the two interoperate. And you can indeed actually sort of even over a boundary of non-.NET code catch an exception that was raised elsewhere. Go over here, back here.
How much of a speed hit is there of this versus C++? I mean, I know there's all sorts of issues, but in real life right now, what's the range?
Well, yeah, like anything, it really depends. I tend to use the number 10%. This is 10% slower. I will just generically fling out. And of course that's bogus. I mean, because it really depends. Sometimes this code is faster. I've seen plenty of benchmarks where we run faster than C++. Certain things actually will possibly run faster because, the jitter can optimize for the particular CPU that you have, versus statically compile for, the x86 family, right? Other things slow you down, like mandatory type safety. Of course, there's a cost to it. We have to check all array indexing. The jitter will do what it can to hoist those checks out of loops, but in a lot of cases it can't do that, and so there's overhead. But then you also sort of get into the less identifiable benefits, there's the notion of raw performance given infinite time and infinite intelligence. Could you write something that was faster in C++ than in C#? Probably yes, in all cases. Now, given the average programmer and the amount of time he has available, it turns out that you get a lot more time to focus on your algorithm because you're doing so much less housekeeping in a managed world with garbage collection and where we cleaned up all of the COM stuff, this low-level stuff that you had to deal with before. So it's a complicated trade-off. But on the average, I think, this stuff does very well.
related question to this. There's certain areas in languages like this that are worse, that are well known to be worse. Like, for example, there's an old rule in garbage collection systems: avoid doing certain things with strings. Do you have a list of sort of areas where you say, well, be careful here, or
we do have, yes, we do have. I don't have the URL on me, but off of the URT site, there is some design guideline documents that we give our programmers that talk about specifically, like, yeah, don't be adding a lot of strings together if you can use a buffer and put them in there instead. I would add though that the garbage collector is pretty incredible. We've done. I mean, everybody starts out with this knee-jerk reaction that goes, I don't need no stinking garbage collection. You know, I want to do my own memory management. I can do it faster. I know I can, you know. And then you run the numbers, and it's pretty incredible. I mean, you know, on a whole sort of slew of different applications, from, you know, apps that allocate tons of objects to apps that allocate fewer, to apps that not just allocate tons of objects, but have incredible depths of stack and therefore, you know, are more expensive to GC. The average time it takes to allocate and collect an object with this garbage collector is about 40 to 50 clock cycles. And of course, it's I mean, first of all, that's faster than most memory managers I know of. And second, the thing is probably the first industrial strength, scalable multiprocessing mark and sweep collector I've ever seen. I mean, it will actually run the GC thread on a different CPU in a multi-CPU scenario, and you might not even know what's going on. I mean, you'll never be able to measure it. The other thing is that it's a generational GC, unlike at least, yeah, in our Java VM, I don't think we ever got around to having a generational GC. And so, you know, short-lived objects get collected at very low cost. So maybe enough about the GC. Yeah.
You mentioned bytecodes and verifier. How does that fit into the language? Is that part of the platform? Or?
Is it part of the? Yeah, it's part of the platform. Yeah, it's part. Yeah. So the .NET framework defines what we call MSIL, the Microsoft Intermediate Language, that all of the .NET compilers emit. And then we have options that allow you to control. First of all, when does compilation? Well, first of all, we never interpret this code in this platform. This platform always runs native code. There is no interpreter. So everything is always compiled into native code at some stage. The question is now, where do you put the dial? You know, with C++, well, it's put at source code, right? The minute you run the compiler, you make native code out of it. And you can still do that with .NET. But you can also emit IL, and then at install time, you can compile the code. So that happens once as you're copying the files, you know, and installing the code. Or you can do it as late as possible, i.e. at runtime, you know, right before the method runs, it's JIT compiled. And then to allow you to treat the dials even further, we have various JITs. You know, we have an econo JIT that is optimized, that's actually what they call it, that's optimized for small footprint and small memory consumption. And it's really sort of just one step up from an interpreter. It takes the IL stream and just turns it into a bunch of calls to helpers, pushes and calls. And then it may indeed throw the code away right after it runs it. But it's still better than an interpreter. And then we have the regular JIT, and then we have this thing called the op-JIT, which is, you know, based on the back end of the C compiler. And so it does, you know, it does as great of a job as the C compiler does. And you typically wouldn't run that dynamically. You'd run it at install time.
So I assume this verifier doesn't do anything for unsafe, but it still lets you load it.
Yeah, I mean, so that's actually a different orthogonal issue, is how is the unsafe code tied in. And whenever you use unsafe code, you have to, in order to pass verification, well, first of all, the unsafe code will never pass verification. So if the verifier ever kicks in, it'll disqualify the code from running. However, you can put an attribute on your assembly, as it's called, which is sort of, you know, the physical conveyor of the code, that says, warning, here lies unsafe code. And at that point, if you have full trust, then the verifier will allow that unsafe code to pass through, but only if you're in a fully trusted context. So this is not something that could be accidentally downloaded, for example.
So for a compiler, it's very important to know what side effects can happen in order to reorder code. So do you have precise exceptions? Do you have imprecise exceptions? Do you have both? And what is the issue with the multi-threading thing? Like?
Okay. So there's a limit to how much code motion we can do in the compiler because we expect the language to have precise exceptions, meaning that an array indexing operation occurs in precisely this order. First, check if that is null, then check this is within bounds, then store, then da-di-da-da. However, the execution engine gives you certain options to relax that from a JIT perspective. So the jitter can be free to hoist array bounds checks out of loops if you loosen, the strictness of your exception reporting. We still have not really determined whether we want to where exactly do we put that thing? It's obviously not, some sort of slider that the user wants to mess with, So how do we express it? We don't know, but the capabilities are there in the runtime.
How about multi-threading again?
You mean with respect to exception reporting, or
exception to access of common data? How do you make sure that a write by one thread is actually seen by another thread?
Don't know the answer to that one. So you should. This is something you should ask the JIT guys probably.
Oh, this is not a compiler issue. It's a language issue.
Okay. Then I don't quite understand the issue.
If you have two threads, one writes to variable A and writes to variable B, another one reads A and B.
Right.
Are they is the order fixed? Can you see the change to B without seeing the order?
Okay, we don't currently say anything about that. Other than, are you asking whether the loads and stores are atomic operations or whether they can be broken down into, whether
it's
you
really
can,
the semantics of multi-threading programs. How do they generally, what kinds of guarantees do you have?
Okay, no, we do not stipulate any guarantees currently. Other than the fact that you can place semaphores and of course control, access to a particular variable or whatever, or serialize it, but that's about it.
So do you allow whole program optimizations, or is it necessarily separate compilation?
We don't give you. The C# compiler itself doesn't. However, since we produce intermediate language, it is indeed possible in the future, but it's not there currently, for our most aggressive JITs to do whole program optimization. It's not something we currently do, but it's something you can imagine in the future. I'll take maybe two more.
So you have this fixed keyword that allows you to capture a pointer.
Yeah.
Do you have other things? So there's sort of a scoping thing there, stack-like scoping. Do you have other primitives that allow you to say, capture a pointer and keep it because some unsafe code is going to hang on to it for a while?
Sure. It's actually, that's not a language feature, but you can programmatically or imperatively fix an object through an API in the garbage collector. Although again, that comes with big fat warnings, because you're creating islands and whatever, and you really, really don't want to be doing that. So was there one last question? Yeah.
You talked about trying to get one last feature in, but it makes me wonder what the schedule for rolling this out is.
The new way we talk about this is we're saying we'll ship it when it's ready. When you tell us it's ready, which probably will be sometime next year.
So did they hand out a beta at the PRC?
We handed out an alpha at the PDC. Our first beta is due, I think, in 2 or 3 months. And then that's beta 1. There'll be a beta 2, and then finally, we'll ship sometime next year.
Are they targeting on including this in one of the platforms that Microsoft's going to?
Well, the first ship vehicle will be Visual Studio, but then ultimately, this thing ideally will be ephemeral. You know, will carpet bomb. Well, it'll be everywhere. You know, go out with the browser and you know, the OS. So that's the plan. All right. Well, thanks for coming.